It helps to unmute when you're doing a webinar. Hi, I'm Eric Smalling. We're going to get started here in just a moment as we let a few more people file in. Actually, it looks pretty stable. I think I'm going to go ahead and get started. So welcome to Hack My Misconfigured Kubernetes, a webinar by Snyk. I am Eric Smalling, Senior Developer Advocate here at Snyk. I've been here for, I don't know, about 8 months now. My background, just so you know where I'm coming from, I'm a software developer by trade. I've been doing it for, depending on how you look at it, 20 to 30 years. I'm in the North Texas area in the United States, so it's bright and early here. I have, for the last decade or so, been a consultant doing a lot of DevOps work, automated test and deploy and all that good stuff. I've been using Docker since the early days, back in 2013 when it was pretty raw. As far as Kubernetes, I have a CKA that I got about a year ago, and someday I'll get my CKAD and CKS. So I've been around the block, seen a few things. What we're going to talk about today is, to get started, I'm going to go into a short description of some of the potential problems and cloud attack vectors we see out there. Then we're going to go into a couple issues we often see with regard to Kubernetes configurations, including security contexts and resources limitations. Slides to move, there we go. So let's start by looking at why distributed cloud-based systems are complex from a security perspective. One of the most well-known security breaches that's happened over the last few years targeted Capital One Bank. This affected over 100 million users in the United States, ended up having I've heard between $100 and $150 million impact on their bottom line in terms of fees and lost revenue opportunities. It's a good example how misconfiguration in cloud-based systems can be catastrophic from a security perspective. There were a lot of factors involved in this, from permissions and RBAC through misconfigurations in web application firewalls and exploitable vulnerabilities in their applications. But the real takeaway here is that distributed applications we are building now are really significantly increasing in complexity. Lots of different systems which may or may not be under our control. Taken as a whole, this means it's really easy to misunderstand how it's all glued together, and that makes it easy for something like this to happen. So the story over the last decade or so in software development has really seen the boundaries of what's an application, what's operations, and what constitutes infrastructure becoming increasingly blurred. The old view of the world was that the application was the only piece under the responsibility of the development team, and all of the other elements of the stack, were usually under IT operations, or with, and with security usually a step right at the end of the deployment process. The world we live in today is one where the infrastructure and workloads are completely tied together. And GitOps, for example, is really an expression of how intertwined those things are now. Everything is declared as code. Everything is a software development practice. And there's really no difference between our workload and the computing infrastructure that goes along with it. And by infrastructure, we don't just mean the underlying compute technology, but also the configuration and the operational policies that control those capabilities. So as a community of practitioners, we've discussed in immense detail this blurring and eventual consuming of the boundary between development and operations. But in lots of cases, we really haven't considered how that impacts how we model and practice security. In many organizations, security is still considered to be an external practice, somehow existing only when our applications are deployed and operational. But this really isn't workable in the era of continuous integration and delivery. As we've seen, development-driven teams now have responsibilities for most of our deployment stack, and so this gives those teams a lot more responsibility for ensuring those things are secure. By the time our code and our infrastructure is deployed to production, it's too late to deal with the implications of security issues. We can't slow down that velocity to introduce security gates in the way that things used to work. Velocity and time to market is the clear differentiator nowadays for business to succeed. So that presents us with a set of unique challenges around security. How do we make sure our applications and infrastructure are secure we're working with practices that are evolving into these super fast delivery pipelines. Security still matters, and we've seen repeatedly over the last few years, security breaches can have massive impact on business, both from financial terms as far as bottom line and potential fines and stuff, but also on how much trust we have with the public, especially in the cloud era. Public trust is just as important as our financials. When we start to look at the different elements that we might now be creating as part of our application stack, from the source code that we've created, third-party libraries we might be bringing as modules, Docker files, infrastructure as code, and Terraform. And we're going to be talking a lot about today the Kubernetes configuration. This is a lot for our developers to have to understand, especially in depth. And we have to be able to make assessments about how secure this stuff is. It's a lot just to get it even working, right? So luckily, Kubernetes itself does have some levers built in that we can use to control some of the aspects of securing our clusters. The first one we're going to talk about is security context. So security context is a set of configuration flags that are defined in our YAML files, which control certain aspects of cluster security. A very simple definition of what these flags control would be that they define privilege and access control settings for a pod or a container. And here we have a typical YAML definition for a pod. And we can see that we have a security context section defined, which in this case sets the privilege flag for this particular pod for whatever reason. This allows it to operate in privileged mode, and then sets some capabilities for the pod, which are privileges that are controlled by the Linux kernel. There are a few other flags which are possible in this section too, but in today's session, we're just going to focus on a few of these. So the first place we're going to start is with this privilege flag. Privilege means the container has basically all the things. Processes running within it can do pretty much anything from accessing the host file system to accessing its hardware. It's basically root, which is clearly dangerous from a security perspective. If this pod is compromised, then an attacker can basically do whatever they like. Now, there may be good reasons for running something privileged. Perhaps you need direct access to things like GPUs, or you need to manipulate the network subsystems. But in general, most processes do not need this and shouldn't be running like this. Kubernetes has granular enough permissions in most cases to be able to give containers what they need. And in most cases, running privilege is just the path of least resistance when folks are deploying applications. It's the easiest way to make things work sometimes. So let's take a look at a demonstration of this. What we're going to do here is we've got two apps deployed in my cluster, and one of them is a mock-up of a payment app. It's not privileged. In theory, it's isolated, and it writes files to disk in a JSON format, which will represent our secure data. The other app is running in privileged, and it has a remote execution vulnerability that we can exploit. Now, because these apps are running on the same node and therefore in the same container runtime, their image layers are stored in the same file system. And we're going to see how an attacker with access to the vulnerable pod can access the files of our supposedly secure payment app. So let's jump over to my terminal. So I've already started up. I've got a Minikube instance running, a single node Kubernetes cluster basically, and I have a couple pods with some services in front of them. Let's real quick show you what we have here. We have the payment application, and it's Docker file. The image it's made with very simple. It's just a PHP application. Nothing crazy here. It just starts PHP on port 8080. And if we look at the Kubernetes Manifest for its deployment, again, nothing fancy here. It's basically a single pod with a single container port 8080, and a liveness probe. Nothing really to see there. Let's look at the web tier though. Again, simple PHP application, nothing much to see there. But if we look at its deployment, very similar to the payment app, except that at the bottom, we can see that security context is, there's a security context and privilege is set to true for some reason. Why? I don't know. I'm a new employee. I just started working on this app, and I've been told to look at this. Maybe the original developers needed this for some reason at some time. But what can that do? I mean, how bad is having a privileged web tier? Well, let me show you the app real quick. So let me go over to the tab where it's running. So it's a simple app that basically allows you to upload an image and make a comment about it. So let's do that. I'm going to upload, my name is Hacker, and I'm going to say that comment. Now, instead of uploading an image, I've got a simple shell, a PHP script here. And I know that the text is kind of hard to see in that preview, but it basically just echoes out a pre-tag with a var dump with a command call in it. That doesn't sound good, does it? So let's submit that. And I'm also going to get out of order in my demo here. I like this website, so I'm gonna say I'm gonna donate to them with my super secret credit card number here. Yeah, sure, 10, 25, 1, 2, 3. Okay, so I have donated to them. And let me go back up to the here, and I want to do a inspect element on what got uploaded. So we can see there's an image tag that inside of it has this upload unique ID on the PHP file I uploaded. Let's go back to my terminal now. Oops, I can find the right screen. And I am going to save that. Sorry, just a second, copying from my notes. Oh, I just overcopied what I needed to, sorry. And I have an ingress variable already set up that holds my IP. I need to copy this again. And I am sorry, if I'm going really fast, we have a compressed amount of time here. This recording will be made available afterwards. Also, swing by our Kubernetes, our virtual booth at the Kubecon, and we can give you demos and answer any questions you've got there as well. So there we have my image variable is set. So I'm going to show you, I'm going to jump into this container real quick just to kind of show you the current state of things. Oops. This is what happens when you get into demo mode and you start copy and pasting everything. Sorry. Okay, so we're in the web pod in the container running in there, and I'm going to cd into the temp directory to show you that it's empty right now. Now I am going to simply use curl to call into that URL, which is the upload PHP that we put in there, with an argument that says command equals make dir, that's a space, temp host. Now, if I exec back in, and I'm not going to go into the shell, I'm just going to ls temp, we've created a host file, or a host directory. That host directory is empty, as expected, but we just exploited this remote code execution vulnerability in our app. So we're already in kind of a bad state. Let's do something else now. So that was a mount. I just mounted /dev blah, 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 blah to temp host. If I do my ls again, those are the files on the host that's running that container. Because this container is running in privileged mode, I'm able to do that. So what can I do once I have that? Let's now I happen to know through social engineering or over some means that I'm looking for things like cards.json. So I'm going to do a find on temp host now. And sure enough, I found a few files that are, have the name cards.json. Let's take a look at one of them with a cat. And I'm doing all of this remotely. Not, having to be on the machine. And there you go. Now I did my demo a little bit out of order. I should have put the exploit in after I paid the credit card, but we can see other credit cards that, no, actually it is there. Look at that. I did the demo right. There's my misspelled John Doe there's the credit card we just put in. So because this pod is in privileged mode, the container is in privileged mode, there's all sorts of stuff you can do. We're exploiting the other container that isn't in privileged mode because we found a kind of a beachhead, a hook point we could grab into. So what can we do to stop this? Well, this one's pretty easy. If I open that deployment YAML file and go down here, I just going to make this be false. Now I could just remove the line because the default is false, or I could comment it out or something. But I want to explicitly in my deployment say this is false. This should not be true for anyone in the future coming to look at it. I'm going to apply that. K is just an alias to kubectl. Deployment pod, and you can see the old one terminating. The new one is running. That means that we have a new pod. So I'm going to refresh this and re-upload our exploit to the new container. Oops, click the right button. There we go. And we'll inspect that. And I'm going to copy the new, get my cursor in there. Okay, pasting that. Now let's try this again. So we're going to curl to try to create our temp host again. And let's see. Oops. Oh. Ah, yes. New. This is going to be the ls temp. Sure enough, remote code execution is still there. We didn't remove the vulnerability. But what happens if I try to mount that volume again to it? Doesn't say failure. However, if I go ls, it's still not it's still blank. So let's pull logs on the web deployment pod. And sure enough, there's our permission denied. So by removing the privileged grant to this container, we no longer are able to do that mount command. So the next thing we're going to look at is root containers. Now it's relatively easy for folks to miss that a lot of container image we're actually using are using the root user inside the container. If we don't define a user in our Docker file, then that's what we're going to get by default. All the processes inside that container are going to run as root. This is slightly different than running with a privilege flag, since the container runtime isn't going to give you all the additional capabilities that you get with privileged. And there are some other differences in terms of things like SE Linux, but you're still going to get a bunch of privileges that you may not want. Again, these are going to be there are going to be use cases where we might actually need our containers to be running as root. Perhaps we want to do things with the system itself, add users or groups, perhaps install packages for some reason. Network operations, certain of those need it, work with volumes. But running as root is a security risk. There's plenty of stuff we can do with if an attacker gets access to that computer. We can access files, exploit the network, potentially access other containers, just still not really advised. So how do we manage the need for additional privileges against running, start my sentence again. How do we manage the need for additional privileges against not running everything as root? This is where Linux capabilities are useful. Capabilities are a function of the Linux kernel, and they allow for more granular access, excuse me, to raised privileges. This was designed originally to allow processes that have that need raised privileges while they start up to do things like configure network access, and then once they're configured, they can drop back down to a smaller set of privileges for the remainder of their operation. In the container world, we use capabilities to manage the privileges that our containers have in a more granular way than just granting root. We should always be guided by the principle of least privilege, though. Just give our containers what they need to operate and no more. We can start along that path by dropping all capabilities and then working out which ones we really need and just granting those. So let's take a look at this in practice. I'm going to use the same application, and we are going to, sorry. Let's see, how am I going to do this? We can go ahead, since we already have that exploit in here, I'm going to paste a curl command in here. And what this is doing is an apt-get install of a bunch of tools. I can do this because in the container I'm root, and I can run apt-get if it's in your image, obviously. I have now installed a bunch of tools without having to have shell access. Now, I could have installed a remote shell. I could have done a whole bunch of things. But what I did was installed some network diagnostic tools, including the command IP. So I can do an IPA, and now I can see, oh, okay, the IP address inside the network this cluster is running on, this container is at that IP address. That's interesting. Let's run, let me get the right command here. Let's run Nmap. So Nmap is a network utility for scanning the network and seeing what is available. I'm going to put the IP address of my container in there. So we're going to scan the /24 network. Again, all remotely, all with curl. And now I can see all sorts of stuff. The interesting things like, oh, look, there's a service called payment. That would be interesting to poke around and see what I could get out of that. So you can imagine what all you could do if you got a beachhead, if you got a foothold in a container and you had full access to do whatever you wanted to do in that container. One of the other things I know that this container has, let me just exec into it for simplicity. So let's say I wanted to do one of those curl commands and I wanted to get something down, and say apt-get wasn't available to me, but curl is. So I could go get a shell script from my hacker server, wherever, and have it start doing whatever I wanted to do. So how can we restrict this? Get out of there. Let's open our deployment YAML. Go down here into the security context. I'm going to add a simple block called capabilities. If I can type, and we will drop. And this takes a list, so I'm going to give it. I'm just going to say all. You have no capabilities right now. I'll do an apply. Make sure it's back up. So it is creating the container, and now it's running. I'm just going to exec into this because I don't want to upload the exploit again, but I realize the exploit would still work. Exec IT, web deployments, and this is 84.5. We'll just start a shell in there. So imagine I'm just doing this through curl, but do the same apt-get updates. No, I can't, because now I'm not privileged enough to be able to do it. Even though I am still the root user in the container, those privileges have come in and said, there's things that apt-get needs to do that I'm not going to let you do. And that would apply also even if I were able to get Nmap on here. The network aspects that Nmap needs aren't available because we're not, those capabilities have been removed. Okay, so Kubernetes security context also gives us another way of handling containers and the problem of running as root, and that we can stop them from spawning altogether. We have this run as non-root flag, which determines if containers should run as non-root user or not. We set this flag, the kubelet won't even actually start the container if its image uses the root user as its default. This is generally a good practice, so you actually might want to set up a enforcement with Open Policy Agent, or if you're still using PSPs, pod security policies, which would use an admission controller to actually stop configuration without this flag from being deployed. Let's look at how that flag works, though, in action. Oops. Here, we'll re-edit. Let me get out of my container. Re-edit the deployment YAML, and I'm just going to add the security context, a run as non-root true, and we will redeploy. Okay, let's get our pods. Oh, this time we have a create container config error. Let's describe our pod and let's see what the detail on that is. Web deployments, 5 Charlie. And at the bottom, it's wrapping around here a little bit, but we have there, kubelet says container has run as non-root and image will run as root. So it's saying, no, you told me not to let anything run as root, and this thing's going to try to do it. So I'm not going to let you start. Now, how would you fix this in your application? You would go into your Docker file usually and add a user command to switch the default user. Obviously, you would need to have the user created in the container image. Note that if you do that, Docker will let you use user and then like a string like Eric or whatever as the user. However, Kubernetes needs that to be a UID, a number, because the kubelet has not started the container at this point, so it doesn't have the mapping of whatever that user string would be to the UID it is, and it's specifically looking for 0 or root. So if you start it with a user Eric, it's going to say, I don't know if Eric is root. I'm not going to start this. It's a little bit different error, but it's the same idea. Okay, so let's go back to here. So how are we doing on time? 4 minutes. Let's change direction real quick and talk about resource limitation. This is a different kind of security issue, but it's still important for us to be aware of and be implementing. Kubernetes gives us control over the resources our containers need. The two most commonly specified resources are CPU and memory. It provides two sets of controls for each, requests and limits. And requests instruct the scheduler to aid it to figure out which node to place a pod on, depending on what's available, and limits define the maximum resources the container can use. By default, pods run with unbounded limits, which means they can control as much CPU memory as is available on the node they're scheduled on. If the resources are exceeded, then in the worst case scenario, we might start seeing applications getting killed as we run out of those resources. The important takeaway here is that you really need to be assigning resource limits to your applications. The way Kubernetes handles these two resources is slightly different. In terms of CPU, there's throttling mechanism kind of built into Linux. So we get applications taking a lot of CPU. They're not going to get terminated, or worst case, they're going to get throttled down and performance will suffer in the applications. So it'll all start to run slowly as they hit the limits you've defined. The more challenging resource to manage usually is memory. Memory is a finite resource. When you fully allocate, processes might start getting terminated when they attempt to allocate more. From a security perspective, this means that an attacker potentially take advantage of this to perform denial of service attacks, either blocking users from using the app that's misconfigured, or worse, the apps running on the same node might be affected. So we'll take a quick look at an example of this. We've got a demo, same idea, two apps running. One of them is fine. It shouldn't be affected by other apps. And then a vulnerable app that has a memory leak that we can actually tickle and cause to happen. So clean up, clean up what I had here. Fire up my new app. I'm not going to go through the deployments. There's nothing really interesting in them. They're still starting up. So we have our vulnerable app. There we go. And we have our innocent app. I'm going to tear this off so we can see them both at the same time. Okay, so if I look at the memory status, we see about 4 gig available. This app happens to have a nice allocate command I can send. So I'm going to say allocate 100 megabytes for 5 seconds. And if I refresh over here, that 5 seconds was really fast. Let me try that again. We should see, we're not seeing memory drop. Of course, live demos. Let's be a little more drastic. Let's allocate 2 gigabytes. There we go. So we see that it drops the memory available to the app that it just happens to be running on the same node because we've allocated the memory there. To fix this, we can edit the app1 deployment. And you can see the developer had put these in and then commented them out for some reason. But we're going to say, let's put them back in here, limits memory to 50 megabytes. And we will deploy. And let's go back to our app, refresh. And you can see right away, I'm unable to allocate 2,000 megabytes. I'm unable to allocate even, oops. The service doesn't like when you pull the pods out from underneath it. But I can't even allocate 100 megabytes because I've told it not to let that happen. So I know we're running really low on time. Let me just hit the conclusions. So what are the things you should take away from this talk? Well, The first thing is that for all intents and purposes, our infrastructure and our applications are now basically the same thing. We can't really separate our workloads from our containers, from our Kubernetes configuration. They're usually developed by the same team, and often they're in the same repository. All of our configuration code needs to be considered as having the potential for security risks, although because everything is now declarative, we have lots of possibilities for static analysis on those files. The responsibility for security needs to shift as far left as we can. We need to empower our developers to make decisions about security based on modern tooling and processes, and to educate them about the critical issues in configurations. We also want to leverage automation here, both in our development pipelines and in our production systems, scanning our code, our containers, and our configuration all the way from local development environments through the source code management tools, our CI systems, and into production. Although we've looked at a few of the issues that you might want to think about around Kubernetes security day, there's a lot more we didn't look at. RBAC, pod security policy, which happens to be being deprecated and replaced, so you might want to research that if you're using PSP. Policy enforcement, compliance in general, network policies, other settings available. Go read the docs. Go to kubernetes.io, read the docs, look at our blog. We've blogged about security context a lot lately on Snyk blog. And tools like Snyk can help you here. We support scanning Kubernetes YAML files through our infrastructure as code product, along with Terraform and Helm charts, as well as container images, scanning code for your vulnerabilities in your third-party dependencies and in your own code. All you have to do is go sign up for a free Snyk account. You can do that. While you're attending Kubecon, you can also drop by our virtual booth, come ask questions. My colleagues are there manning that. They can give you demonstrations tailored to it. You can find me on Twitter and LinkedIn, and I'm sorry I ran a couple minutes late, but I hope you enjoyed the talk, and hit me up with questions. I will look forward to your tweets and messages. Have a good day.